This is lecture 31 on line integrals. This follows roughly page 332 to 335 of the 2020 notes. I think in the edition I have printed out here, I had still grouped the material on curves, paths, reparameterizations and such, and the scalar integral. So I'm skipping past that because we did that earlier. Remember, we already introduced the integral along with respect to arc length, and we proved that the integral, as defined by, evaluate the parameterization times the speed, evaluate the parameterization times the speed, that defined the integral with respect to arc length. And we proved, among other things, like that integral doesn't care if the curve is reversed. Today we're talking about the integral, not with respect to arc length, but with respect to the so-called line integral. So here we're integrating the vector field f along a curve. And so you may know from physics that if we have a force applied over a distance, then work is done, right? So force times distance equals work, the most naive thing. But then if the force is variable, then we need integration, right? And furthermore, if the force is perpendicular, then it doesn't do work, right? So only the part of the force that lines up with the direction of motion does work. And so put that all together, you get the work done by a variable force field along a curved path, and that is what is captured here by this definition, is the work done by the force over the curve. Now, of course, it doesn't have to be physics, right? This is also a mathematical definition, and this is the so-called circulation also. We can think about it as being the circulation of the vector field. I think I've got dust on my screen. It basically measures how the vector field lines up with the curve, and the more the vector field lines up with the curve, the larger this integral is. If the vector field is always perpendicular to the curve, then see, this is the velocity vector to the curve, right? So if the force is perpendicular to that, then this is 0. So if the force lines up with the velocity vector to the curve, then this is larger. Now, one of the things you want to know about is what happens if you reparameterize, like this integral. The definition I just gave you is in terms of a specific choice of parameterization for the curve, right? And so what would happen if we used a different parameterization, right? That's a question that we must ask and answer, because if the answer is that we get different work done, then that's not a good definition, because, well, then how do we know which we're using the right parameterization, right? Well, it turns out, though, that as long as the parameterization is consistently orienting the curve, which means that the reparameterization function is strictly increasing, a1, b1 to a2, b2, then let's see here. So I start with the integral setup with respect to parameterization 1. I rewrite that t as u of t and gamma 2 of u of t, so I'm reparameterizing the curve with this new parameter u. And then by the chain rule, I get the gamma d2 du of u of t times du dt. But then the thing is that that's exactly what we need. In some sense, the dt's cancel, formally speaking, but really what I'm using here, going from here to here, is the u substitution theorem, which says that you can change from dt to du if you've got du dt multiplying, and also you have to change the bounds from b1 to u of b1 and u of a1. But there you go. This is the work done with work calculated, or the line integral calculated with respect to parameterization 1. This is the line integral calculated with respect to parameterization 2. They're equal. But this assumes that the reparameterization takes the lower endpoint to the lower endpoint and the upper endpoint to the upper endpoint. When we talked about reparameterizing, when we talked about reversing a curve, these get flippity-flopped. And so if you had a disorienting, if you will, or a orientation reversing parameterization, then instead of parameterizing c, you'd be parameterizing minus c, and then like du dt would be negative is the main thing. The du dt term would be negative here, and So, well, actually, du dt doesn't have to be negative. That's not it. Well, yeah, du dt would be negative. I'm sorry, guys. But everything else here, I mean, this would all still go through, but there'd be an extra minus from the fact that du dt was, well, oh goodness gracious. Sorry, I've lost my place. If u is orientation reversing, then we have u of a1 is equal to b2 and u of b1 is equal to a2. So when we calculate this, we get to the minus is because I have to flip the bounds to get them back like that. In any event, we can see that the integral of the line integral with respect to minus the curve is minus the integral. So in other words, if you reverse the curve, you change the work done by a minus. So in short, the line integral assumes that we're calculating with respect to an oriented curve. It has to be given a sense of direction. And I should also mention that we can recapture this formula here in terms of an integral with respect to the arc length. And here's how you do it. Integral, the line integral by definition is that, but we can rewrite velocity as velocity divided by speed times speed dt, assuming that it's a nonstop curve, right? And then this right here is a quantity. What is the thing in square brackets? Well, the thing in square brackets right there, that's velocity divided by magnitude of velocity. This is what we've called before the unit tangent vector, right? So it's the unit velocity vector. And then that's speed. So what we're looking at is some function times speed integrated across speed times over time. Well, that's the arc length integral of f dot t, because this is f dot t. So in other words, another way to look at the line integral is it's the integral with respect to arc length of the tangential component. That's what this is right here. Tangential component of the force. And so we can in fact write the line integral as an integral with respect to arc length, right? Which at first glance might seem controversial, because remember I just told you that we proved that integral with respect to arc length, I mean, this is a theorem that I have proved before, is that the integral of a function with respect to arc length over curve is equal to minus the integral, the integral of the function over the reversal of the curve ds, right? But there's an assumption in the proof of that theorem right here, this result, is this assumes f independent of c, essentially. So the assumption is that the function is not going to be altered by the way you parameterize the curve. And of course, in the context down here, if we reverse the curve, then the tangent vector is likewise reversed. And so that's where the minus comes from. It doesn't come from the integral with respect to arc length, it comes from the fact that the unit tangent is reversed if we reverse the curve. But anyway, here's an example. Calculation. So here's a force field, and I take an ellipse on the plane, z equals 1 minus x minus y, where x squared plus y squared equals to 4. In other words, the ellipse is formed by the intersection of the plane and the cylinder. And I say orient c counterclockwise direction relative to xy plane with positive normal. So imagine you're pointing your hand above the xy plane and your fingers curl around the ellipse in the counterclockwise direction. So in short, I have to figure out the parameterization of that curve, and to do that, I start by attacking the circle equation. I put x equal 2 cosine t, y equal 2 sine t. That'll match up with the curling of the right hand I was just mentioning. And then to find z, well, z is 1 minus x minus y, so I'm just going to plug these formulas into the plane equation, and that should do it for us, right? Z is 1, sorry, I'm trying to get things in frame here. I don't know if my eyes are fuzzy or if the camera's fuzzy. If the camera's fuzzy, my apologies. I don't know how to, I'll have to find a lens cloth or the cloth or something. I don't know if I have one on hand. So z, the parameterization of z, would then be 1 minus 2 cosine t minus 2 sine t. And so there we go. First order of business, we found a parameterization of the curve that we're integrating over. Then I calculate the velocity by differentiating. And then I evaluate the function at the curve. So I have to plug in this for x, that for y, and 2 times parentheses sine t minus cosine t for z into the formula for the force field. And when I do that, I get this. And then I take f of r of t, which is right here, and I take the dot product with the velocity, which is right there. And, okay, so, sorry, this is the force evaluated, the parameterization, this is the velocity. So force dot velocity, and you do some algebra, and it works out to cosine 2t actually, and when you integrate from 0 to 2 pi, you just get 0. So it's not a especially exciting example, it works out to 0, but that happens sometimes. And anyway, the above example indicates how we apply the definition of the line integral directly. But sometimes in science and engineering, we have another notation, a so-called differential notation that you'll see a lot of people use. Essentially, it's tied to the integration of the differential forms p dx, q dy, and r dz. In particular, people like to define, what's meant by the integral of p dx or q dy or r dz. P dx is that, the integral of q dx would be that, integral of r dx, r dz. dz, dx, look at this, dx, dx, good night. That should be dy. Sadness, that should be dz. Alright. Okay. So these are, how we define the integral of these differential forms, just by plugging in the parameterization and converting the dx to dt as appropriate. Essentially, that's like the mnemonic here, the heuristic for these formulas. And of course, if you add these together, like this plus this plus this, you get that plus that plus that, which you can factor out p comma q comma r dot dx dy dx dt dy dt dz dt. In other words, if you add this integral, that integral, and that integral all together, you get the line integral again, the work done by the force. Here's the formula. So the integral of pqr dot dr is the integral of p dx plus q dy plus r dz. So this is kind of, sometimes this is a more convenient way to think about the mechanics of calculating a specific line integral, as I'll show you in a second here. Here's an example, integral of f dot dr of y comma z minus 1 minus plus x 2 minus x, and I give us parameterization for the curve by x is cosine, y is sine, z is equal to 1. So in this context, dx is just minus sine t dt, dy is actually cosine t dt, and dz, well, z is constant, so dz is 0. So when I'm integrating f dot dr, that's the same as integrating p dx plus q dy plus r dz. And so when you plug in, evaluate p at y, p is sine t, q is ends up being cosine t, because z plus x is cosine plus 1, and cosine plus 1 minus 1 is just cosine. And then r is 2 minus x, which in this case is 2 minus cosine t. But then in some sense doesn't matter because dz is 0, right? So p dx plus q dy ends up being this, which is the integral of cosine 2t dt, which is 0 again. And you might start to get the idea that whenever we integrate around a closed curve, it's 0. That's not in fact the case. Let's see here. How about this one? Yeah, the next example. I have integral. This is a two-dimensional example, which is good. Y comma minus x, and I look at a circle, radius r, parameterized by r cosine t, r sine t. And so p dx q dy, in this case, the y is r sine t, and the dx is sorry, I didn't put the y in yet. I left it as y. And the next calculation, I'll put in the y is r sine t. That's why I changed from sine t dt to sine squared t. And anyway, long story short here, we end up with just sine squared plus cosine squared, which is 1, and there's a minus 1 that we factored out. So we get minus r squared dt is p dx plus q dy. So when we integrate this thing from 0 to 2 pi, we just get minus 2 pi r squared. So here's a vector field that when we integrated around a circle, we got something non-zero, because actually if you pictured this vector field, you'd see that it kind of wraps around the circle in the same, well, actually in the opposite direction of the circle because of this minus. So yeah, just because we integrate around a loop, it does not mean the answer will be 0. All right. And in fact, well, anyway, I could say more about the previous example, but I'll shut up. And here's some properties of the line integral. Integral of a sum is the sum of the integrals, pull constants out, and if we have the union of two curves, then we can break it up into the sum of the two integrals of those two curves, which are joined. Not surprising. And I took a couple minutes here to write out another example for you guys, because I thought it might be helpful. So here's a bonus example. So here I have the vector, I'm integrating xy dx plus y plus z parentheses dy plus x dz, where this curve 1 is given by x equals to t, y equals to t squared, and z equal to t cubed for 0 to 1. So how do we calculate this integral? Well, by the way, before I do that, this is equivalent to calculating the work done for the force F, where F is equal to xy, y plus c, and x. Like this line integral is that. Just the same, all right? And so to calculate this integral, we can just basically differentiate the parameterization, the parametric equations rather, and basically take the total differential of each parametric equation. That gives you the corresponding differential relation between dx dt and dy and dt and dz and dt. And in particular here, we've got dx is dt, dy is 2t dt, and dz is 3t squared dt. And then you can just think about plugging in this, and this into that, and that. And likewise, evaluating x, y, y plus z, and x at this, and this, and this appropriately. And when you do that, well, this happens. So you get, xy is t times t squared, and dx is dt, y plus z, t squared plus t cubed, dy was 2t dt, and x is t, and dz is 3t squared dt. So there you have it. And then just do the algebra, and when you do that and put everything together, I get 43 over 20. Now I thought it would be interesting, basically this is a twisted cubic, it's some kind of like curvy thing that starts at the origin, and when you put in t equal to 1, you get 1, 1, 1. So this curve has terminal points, the origin and 1, 1, 1. It ends at 1, 1, 1, right? So another curve we could think of that goes from the origin to 1, 1, 1 would be the line segment. So C2, I call that C2, and the equations for the line segment from 0, 0, 0 to 1, 1, 1 would just be y x equal to t, y equal to t, z equal to t for 0 less than t less than 1, right? And so I thought, well, let's calculate the integral of this force over that line segment instead. And when I do that, I end up with this calculation. And interestingly, the answer is not 43 over 20. This time it's 11 over 6. So as you can see, for a given force field in the same pair of initial and final point terminal points, we can get different line integrals, right? So generally speaking, line integral depends on the path taken, going from one point to one fixed starting point to one fixed ending point. The work done will depend on which path we choose for an arbitrary vector field. But the kind of vector field we talk about in the next section, conservative vector fields, have the unusual special characteristic that it doesn't matter which path you go. Like a conservative vector field, among other things, will be one for which, if you integrate you find the work done along a path from initial point to a final point, the work done will be independent of the choice of the path between the points, for a conservative vector field. Anyway, more on that next time. Thanks, guys.